Yeah, I'm happy to see that some people are also interested in what I have to say. This is very nice. This is the very first experience for me, actually, giving such a talk, but I'm super excited. So yeah, as mentioned, I will talk a bit about ice shelf or glacier ocean interactions in fjords around Greenland. So we're going to travel to the very north of Greenland, actually, to the Ryder Glacier. It's in the northwest of Greenland, basically. But I'm going to show you a map later on. Yeah, I would say we can jump right into it. I'll give you a quick overview of how I'm going to get this topic to you. So I'll start with some physical basics just to make sure we're all on the same page here and I don't speak gibberish to some of you. I think that's a good idea. Then I'll show you a bit of an observed reality, or as much as we could observe, basically, or colleagues of me could observe. And then I'll go into the modeling part. So as mentioned as well, I'm using a very high resolution regional model to model these interactions and circulations next to or under the ice shelf. And basically, I'm going to take you through my first year of my PhD, how I developed this model, starting from very simple configuration to something that's not quite yet a fjord, but has some resemblance, maybe. We'll see. Okay, so just as a quick introduction, this is a paper, or from a paper that came out just this year, showing where ice sheets around the world basically lose their mass. So we're going to be all the way up here. Can you see my pointer? Perfect. Okay, so we are all the way up here in the north. This is where my glacier is. But this is not the only glacier that is actually marine terminating, so ending into the ocean. And if you get the water to the glacier, there's obviously some stuff happening. And especially now in climate change, where we all know things are warming up. Also, the water is warming up quite a bit. And well, that warmer water melts ice. I think that's common knowledge. So yeah, there's a lot of stuff happening right now and changing, in fact, and we will be trying to model some of these changes. All right, but I want to start with the basics now. So one thing I want to just make sure that there's no, that this is clear. So we have basically two types of ice in the ocean. One is the typical sea ice. That is what you find in the North Pole, for example. So this is where ocean water basically just freezes and builds a cover over the ocean. And the other one is called shelf ice. And that's what basically comes from glaciers. So it's a glacier that ends into the ocean and then forms kind of an ice tongue that reaches over the water. So there's water underneath as well, and it's kind of floating. But just to have a scale, so what you see here on the ground, this is basically sea ice, so just frozen ocean water. But this large stuff here, can be from, I don't know, I would say this is about 2 meters thick in total, but this can be up to 20 or hundreds of meters high, basically. It's technically mountains at some point in some regions, or around Antarctica though. But those are two different kinds of ice, basically. And I will be talking about the shelf ice, so about this big stuff, and how in the region underneath this shelf ice. And now I have two physical principles I just want to go through very quickly, because that's basically what my work is based on. And it's the principle of density and buoyancy. So density, some of you probably have heard. It's about the denseness or the weight of stuff, and the buoyancy is basically the opposite. Buoyancy describes how well something floats, and ocean water has basically two important properties. That's temperature, that's kind of clear, but you all know also that the ocean is pretty salty, and if water has different salinities, it also has different density and therefore also different buoyancy. So fresh water is lighter than fresh water is water that is not salty. So fresh water is lighter than salty water, and warm water is lighter than cold water. But I think that you know. So I have basically two illustrations. One, you see a temperature field here. So we have warm temperatures on this side and cold temperatures on this side. And what will happen is that the warm water here, you see that that's velocity arrows basically of the same area. You see that the warm side of of this box basically has a rising motion. So up is up in this case actually, and on the cold side we have a downflow, basically a sinking motion. And you can do the same thing, but for salinity. So now I have very saline water on the right-hand side and fresher water on the left-hand side. And as you see now, the very salty water or saline water will sink down and the fresher water will go up. And then you have a circulation. This is called the buoyancy-driven circulation, basically. Okay, now we have these concepts clear. I guess we can start now with the observations that were made. So those, what I'm showing here is also a very, very new paper actually from Martin Jacobsen. He's also at Stockholm University at the geophysics department. And they went on a cruise together with one of my supervisors in 2019. And they went to Ryder Glacier all the way up north to Greenland, and they took some measurements. And this is basically the sketch or the schematic that came out of that. So it has a lot of information here. So I'm going to go through it basically bit by bit. So first, what are we actually looking at? What's the region we're looking at? So you imagine, I mean, maybe you've been to Norway before and you've seen a fjord, but I guess all of you know what a fjord is. But what we see here is basically a cut in the middle of the fjord along the longest axis, basically. So on the left-hand side here, we have basically the end of the fjord where it meets, usually it meets land. In this case, it meets the ice. And then here on the right-hand side is the open ocean. So the fjord ends at some point, spreads out, and then there's ocean. Which already, so yeah, I already said that, but that on the one side we have here the ice. So here it's a glacier that ends here, and the ice kind of reaches over as like a tongue onto the ocean basically, and builds a cavity underneath it basically, where the ocean water still flows. We have here at the Ryder Glacier and at some other glaciers too, we have a very interesting feature, and the sort of sill. It's like not a hill, but like a barrier. You can kind of imagine that the lower part here is kind of a bathtub. So it's really, really enclosed kind of, and water can only leave by basically overflowing the bathtub. And other way around, it can also only enter by overflowing basically into the bathtub as well. This is a very interesting feature because, as you can see, the colors here kind of indicate temperature. So we have this warm AV, since for Atlantic water, we have this at the bottom here. But due to the sill, this warm water cannot protrude into the cavity actually. So we don't get that warm water towards the ice, which technically is a good thing, right? Because if it's not getting too warm, it's not melting too much. At least that's kind of the idea. So taking measurements in these kind of environments is super, super hard. You kind of take a ship, an icebreaker, and try and go there. But obviously you can go close to the ice, but you can never go under the ice really. So everything that's underneath here is, so sometimes what people do actually, they drill through the whole ice. But as you can see here, this is like 400 meters thick. And then there's also some on top. So this is a lot of ice to drill through just to take some measurements. And then you have only one. And you kind of want more, but so what's shown underneath is kind of guesswork, and that's why I put the reality in I forgot what they're called. Sorry. So it's only a very good guess of the reality, because we also know kind of the theory behind it, and we know how in theory the water should flow and look like. So we can make pretty good guesses. What we do not know quite yet is this part basically, and that's the part I want to model now. So as I said, we know a bunch of equations that kind of explain how the water and the ice interact with each other. It has not really been measured because it's hard to get there. Also, you then only have one measurement, and to get really close to the ice is kind of difficult. So we decided we want to try and model these interactions. Are there questions so far?
I would have a question.
Yeah, Matthias.
Is it, so if I understand this graph correct, is it not possible to go with a submarine or something under the ice?
That is a very good question. So I think most of them, I think it would technically be possible, but it's probably super expensive to take like a huge submarine to go under there. What is done right now is they try to build autonomous submarines, basically. They're called gliders. and then they're called deep sea gliders, basically. But it's super hard for them to navigate down there, because if they are autonomous, or also for an actual submarine, actually, you do not, since there's an ice cover on top, you cannot really communicate very good, right? You would have to need you would need some kind of sound source underneath the ice somewhere that has a precise position and doesn't change position, in order for you to ping that location to be able, so that you know where you are, because otherwise you might get stuck under the ice and not be able to come back, and that's dangerous, I would say.
Okay, thanks.
Yeah, sure. Perfect. So far to the reality. Now I'm going to start with the model, and as I said, I'm going to basically walk you through what me and there's a second PhD. His name is Stefano. We work together on this model, basically, and he does all the math stuff, all the difficult computational stuff and coding stuff, and I only use it afterwards. Okay, but so we started out with a simple box similar to what I've shown before for the buoyancy. We basically take a box that's 1 by 1 big. It doesn't even have dimensions yet, so it's not even 1 meter or 1 kilometer. It could be one of anything, basically. It could be 1 apple by 1 apple. But we know we do have a vertical axis and a horizontal axis simply by putting gravity in there. We know that one is up and one side's up, one side's down. So we have a vertical and horizontal dimension in this case. And then we have these equations that I already talked about. In our case, they're called Navier-Stokes equations. And they basically describe how pressure, velocity, salinity, and temperature should change in theory in a body of water, for example. Right. So we have a mesh. In our case, we have a mesh or a grid that's made out of triangles. That's called the finite element method. So in the most ocean models, or models in general, also for the atmosphere, you would take rectangles. But now we took a new approach to use these finite elements. It makes things a little different, but in the end, it's all modeling, and the equations are the same. Of any temperature, basically. In this case, we chose just 0 because we want to test some physics. I hope you can hear me all right, because just said my internet connection is unstable. But let's hope for the best. So we want to do some testing of the physics if our equations are correct in the computer. Now, what we start out with is called lid-driven test. So as I said, this is up, this is down, so you could kind of see this is like the lid of our box. And what we do is we kind of pretend there's a wind blowing above the box. So we prescribe a velocity at the top level, and then we can check what happens in the rest. So we prescribe basically this yellow line. It's technically arrows that are lined up towards at each other with the velocity of 1, and they just blow across the lid, basically. And what happens is just due to the equation we gave the computer can calculate this kind of circulation, which makes sense, right? So we push all the water to the right boundary, and since it's closed there, remember it's a box, it's closed there, the water has to go somewhere. Since it can't go up because there's also the box closed there, it has to go down. So we have a downward branch. And on the other side, basically, where the water is pushed away, you kind of get a vacuum, kind of. So you get water from the bottom sucked upwards. So that seems all right. For us, we would say, okay, model, you're doing good work. That all makes sense. Plus, there's also a bunch of papers and older work you can compare it to check whether or not your model is actually doing good things. There's a second test, and that's called the buoyancy-driven cavity. That's basically what I've shown you before. So you have a temperature or salinity field that you prescribe. So yeah, we tell the model, okay, I want temperature on this wall to be 1, on the other wall to be 0. Now tell me, what do you think the velocities look like? And the model says, okay, if it's warm, water goes up. If it's cold, water goes down. Great, model doing great work. This is obviously super simple to now, but those are important checks just to make sure that we're actually doing good things and the model is actually correct, because we kind of want to infer from that for bigger processes. Right. Another test we can do. Now we're getting a little more fjord-like, actually. So our domain is not a square anymore. It's only one high, but now it's 100 of still whatever. It doesn't really have dimensions yet. And 100 across. So in horizontal direction, it's 100. It's 100 by 1 basically. And as we've seen in the actual real fjord, there's somewhat of a sill or a bump in the middle. So we try. Okay, we also put the bump in. And then what we do is we prescribe a temperature stratification, it's called, or temperature layering, basically, where there's warm water on top and cold water at the bottom. And just from intuition, we would say, okay, if the warm water is on top and the cold water is at the bottom, that seems all right. That should stay exactly that way, because cold water is heavier or denser than warm water. So we tell the model, this is what it looks like. Here's your temperature. What kind of velocities does the model give us? And from expectations and sanity, we would say actually no velocities. So then this happens. So we get a bunch of arrows here, which basically say, okay, but the model kind of thinks there is velocities. But if we now look at this color, this is the color bar kind of indicating the strength of the velocity. And it says 1e minus 5, and just translate into real numbers. 1e minus 5 means basically 1 divided by 100,000. So 0.00001 of whatever. I don't know if you've noticed before, but before in the buoyancy-driven cavity, for example, we had velocities of about 3, just 3, no e, no minus. So these velocities we're seeing here are super, 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 super small. And this is actually something we can live with, because this happens in every ocean model, actually. This is called the Ford test. And these errors are basically due to, let's see, can I get back, go back some? Yeah. Because our lines here are kind of bent. So we see that the left and the right, the lines are either straight vertical or straight horizontal, and then we have the diagonals. But if you go towards the middle, you see that they are not horizontal anymore. And this induces an error, basically, which the model cannot quite, let's say, comprehend. So the model understands this error as there's actually a velocity. But this is totally normal for all the ocean models. And since it's so small, we're okay. It's fine. Model is doing a good enough job, basically. So what we do is we say, great, that's good enough for us. We continue. Now we get a little more complex, something that's maybe a little more fjord-like. So from the observations, we now go towards the ice side of the fjord, basically, all the way to the left. But we have to simplify a bit. So what I did here is basically, I tell the model this wall is ice. There are a bunch of equations I can give the model to say, okay, this is ice, and then it will calculate some interactions or changes of the ice due to the water. For example, melting, and then the melting induces fresh water because ice has no salinity. But if I melt the ice, there's water with no salinity, and if I mix the two, I lower the salinity. And you can see that here, right? It's a little darker blue or dark blue here. So I have lower salinities at the ice wall. That makes sense. That is good. And just to make sure that my model keeps salinity, I just do the opposite, basically, on this side, and just say, okay, on the right-hand side, I always want 35 salinity, always. And then the model, I start running the model, and it starts calculating and gives me a velocity field that looks something like this. And this, to us, makes a lot of sense. So we can go through it again. So we have here the less saline, the fresher part of the water. And as we learned before, fresh water is lighter than salty water, so it should rise, and it does. So it's great. We have this rising motion here. But now it's kind of interesting. So it rises up, but then it makes this weird kind of bounce back down. And you see it a bit that it's kind of wiggling, at least in the beginning, and it straightens out towards the right-hand side. But this also makes sense. If you think about it, I know you've all been in the swimming pool before, I assume. And some of you, most of you, all of you were kids before, and maybe have played with a ball. And if you push a ball down, and so ball is obviously light and floats, if you push it down into the water and let go, it'll basically bounce up, but then swing a bit until it's stable in the water again and doesn't move. And the same thing happens here. So we have a lighter version of water, or lighter box of water basically that just rises up in the water, but basically overshoots the height where it would be stable. So it has to come back, because then it is in a regime where it's all of a sudden heavier than the surroundings. So it has to go back down. But then again, it kind of still has its speed, and it's not stopped fast enough. So it goes down too far and then goes up again, and then kind of wiggles until it's at a more or less stable position. And that's basically the position where the water then leaves our domain. So it flows away from the ice, because, I mean, it can't flow into the ice because there's ice. So it has to flow in the other direction. And then, just because what I said, that I want the high salinities here, I have a sinking motion here, which then also basically closes my circulation, because my model is written in a way that I cannot lose water, because otherwise the whole thing would blow up and give me weird results that are unrealistic. So that's basically how far I've gotten with my modeling. Great. So back to the reality. What is still missing? My model is obviously not a fjord yet. I guess all of you were able to see that. So what is still missing? One thing that is missing is the correct ice geometry. So my wall now was just vertical, but you can clearly see that here it's actually not vertical. There are, however, actually also vertical glaciers that basically just end in a more or less straight wall into the ocean. So this is not too bad, actually. But we kind of want to model the Rider Glacier. So at some point we're going to do that. Actually, just today I tried this with another model, but it didn't work. So I have to try it more. But we're on a good path, we think. Okay, another thing that is still missing is that, obviously, so a fjord is not a box. It's open on one side. So there's a bunch of things you can do to actually prescribe an open ocean on one side of the your model domain. This is not as straightforward as it sounds, though. It brings all kinds of difficulties, and I haven't not looked into it too much yet. So yeah, it works somehow. And it will work in my model too at some point, I'm sure of it. And that's basically the question that's super important, that I kind of started out with, like, what actually happens in a warming climate? And that's basically the research question we're trying to answer now. So we take our model that we have, and then what we do is we prescribe basically what we measure here, and then just try and warm up the bottom part of the water, because this is where the ocean warms the most. So the expectations without the sill would be that this warmer water moves towards the ice and then basically just melts the ice faster. But then we see here with the sill actually in it, this warm water is not able to cross over that sill. So we are not even sure if a warming ocean for the glaciers with the sill, or fjords with the sill, will actually really accelerate melting of ice yet. So this is the part that we want to model, basically. What happens? How much does the water have to warm, or how much of the water has to warm that the warm water can reach over the sill, flow into our cavity, and then reach the ice at some point? Because so you can also imagine there's like a feedback loop here. So if I melt more ice, these two layers, and the green layer too, if I melt more ice, there's more water that flows out, but there's only a finite volume of water that can flow through the surface and the sill. So if I have more water flowing out, there's actually less water that can flow in. So that kind of cools down my cavity again. So there's a bunch of things going on that we're not quite sure yet, that could not be measured because we don't measure too much, that we want to model in the future. Unfortunately, I can't show you anything yet because I'm not that far yet. But I have a couple more years left in my PhD, and hopefully at the end we'll be there. And yeah, maybe I can come back next year and tell you how it went. We'll see. But so far I have three takeaways for you. One is that we cannot really observe the complete reality of the ocean just due to, I would say, actually due to money. If I had an infinite amount of money, I would just put a boat there all time and we could measure as much as we want. But we can't do that. But due to physical principles, we can basically make pretty good educated guesses on what it looks like. We can pretty simply actually model the simple physical principles. And that's not too hard. We've seen that with the lit-driven cavity and the buoyancy-driven cavity, for example, also with the Ford experiment with the sill in the middle. The complex part is putting all these different processes actually together. So modeling reality is actually a puzzle of just a lot and lots and lots of small puzzle pieces, small principles that kind of work together or against each other, that then make up a bunch of big processes that is hard to predict actually what they do in total. Okay, and with that, I'm actually done, but I think time's up as well. If you have any questions, ask them now. If you have questions later, feel free to reach out to me on Twitter. I can also post my email address in the chat. I didn't put it on the slides though.